Okay, I did a mistake here from last time. My bad. This is not 0. So I apologize. I was trying to go way too fast because I had so many internet problems the other day. So 0 to the negative infinity, if we rewrite that with positive exponents, that's 1 over 0 to the positive infinity, right? But what did we say 0 to the infinity is? It's 0. So then this would equal 1 over 0. But if we go over to one of the other limit facts that we did, which was number 8 there on your notes, what's 1 over 0 equal to?
Infinity.
Yeah. So that one, my apologies. I just wanted to correct that. After I got done with the lecture, I went, oh, well. So what we did last time, just as a reminder, is I introduced a brand new kind of function, a brand new function called vector valued functions. And we did a little function machine here where the idea is the domain are a set of values of time t that you feed the vector valued function, and his output is a vector. And it'll be either 2D or 3D depending on the vector valued function you're doing business with. Then we talked about the graphs of vector valued functions are curves. They're really not. They're really collections of vectors, but you erase the vectors and you just connect the tips to each other and then you get a curve. And so we were doing some graphing on our graphing calculator using parametric mode of some 2-dimensional vector valued functions, and we did some eliminating the parameter, and then we also did the reverse of eliminating the parameter. It's called parameterizing, which was right here. And you're going to be doing this in chapter 17 when we get to vector calculus, so please know how to do that. Then we looked at domains of vector valued functions, which is the OK inputs, what's OK to feed your vector valued function. And these are all the rules for domains, and it turns out you figure out the domain separately for each component, and then you intersect the sets and to get the ultimate, the result of your domain. Then we did limits, and it's real easy to do limits if you're pretty good at limits from Calc 1 and Calc 2. You separately take the components limits and get a vector. Now, if even one of the vector's components limits does not exist, then the entire limit does not exist. So let's continue on our limits, and then we'll get to derivatives and integrals. So last time we did letter A here, and all 3 of those components did have a limit that existed, and so we put it all together, and our final answer was itself a vector. And so that was nice. So let's keep going. Letter B, what do we got here? Well, if we take the limit as time t goes to 0 of the first component, and this we're just using direct substitution here, I end up with 0 over 0, but that's indeterminate. But it's the kind of indeterminate that you can go ahead straight away and use L'Hopital's. So I call L'Hopital's LH for short. So that means you're still going to take a limit as t goes to 0, but you're going to take the derivative of the numerator and divide that by the derivative of the denominator. Then use direct substitution. Okay, so cos 0 minus 1 all over 3 times 0 squared. Well, cos of 0 is 1, and then we get 1 minus 1 on the numerator, and then we get 0 over 0, which is indeterminate. So now what? Use L'Hopital's. Okay, we just did L'Hopital's. Yeah, but we're doing repeated L'Hopital's. That's legit. So then, okay, well, then what's the derivative of cosine t minus 1? I get minus sine t, and you divide that by the derivative of 3t squared, but that's 6t. And now I use direct substitution. Oh no, I get 0 over 0 again. Oh my goodness. Yeah, use L'Hopital's again. So it turns out this will be the last time, thankfully. We finally see a light at the end of the tunnel. And then when we use direct substitution now, we get negative cos of 0 over 6, but that's negative 1/6. So the limit for the first component exists, and it's negative 1/6. But you're not done, because you have these other 2 components left. Okay, so you take the limit as t goes to 0 of the second component. All right, so then I get 3 times 0 divided by 0 minus 1, which is 0 divided by negative 1. Do I use L'Hopital's on this? What do I do?
Equals 0.
That's 0. 0 over a number that's non-zero is 0. So we have a limit for the second component. Yay. And then finally, the last component, take the limit as time t goes to 0, arctan e to the, what is that, e to the t squared over 2t squared. Okay, so using direct substitution, I get arctan e to the 0 all over 2 times 0 squared. Oh my goodness, so I get arctan of 1 over 0. Okay, now what?
1 over 0 is infinity.
Yeah, now how do I know it's not negative infinity? And I'll give you a hint. This is going to be a positive number. So if that's sort of, this is like 1 over, you know, it's positive 1 over 0. So you're going to get arctan of infinity, but now what?
That's pi halves.
That's pi halves. Bingo, exactly right. So that was kind of an interesting problem because you had to kind of carry through and use multiple limit facts to get to your result. Now your final answer, you better put it all together because I'm not going to give you full credit unless you put it into a vector. So the components are negative 1, 6, 0, and pi halves respectively, and that is the answer for letter B, and we're done.
Cool.
Yeah. So all of the knowledge that you glean from taking Calc 1 and Calc 2 in limits is going to come in handy here. Now, for those of you who are like, well, I still hate limits, and thankfully after this little section is done, I won't ever have to see limits again in Calc 3. Think again. When we get to the multivariable part of this course, we are indeed going to hit limits again. Well, what do you mean? Well, remember I did those 4 modules. There was like a little flow chart last time. I said, okay, congratulations, everybody. You're now graduates of the first module of this semester, chapter 13, where we discussed vectors pretty much. And we're now beginning the second module of the course. So yes, we're going to have limits there, but just to let you know, limits aren't going away. They're going to get harder because you can't even use L'Hopital's when we do limits in this module, which is coming soon. So limits aren't going away. So just to let you know, I want you to be good at limits. And so if you need to review limits from your past, now would be a good time to get caught up. Okay, so how about letter C? What's up with letter C? Well, let's start in and start doing the direct substitution. Now this is a limit at infinity. And so sometimes when you're doing limits at infinity, growth rates sometimes come into the conversation, depending on the problem. So when you took Calculus 2, I hope that you had the idea of growth rates. So in case you forgot growth rates, the idea is certain functions go to infinity faster than other functions. Really? Yeah. Well, for example, logarithms go to infinity as x goes to infinity, but they're kind of slow at going to infinity. So they're slower than, say, a polynomial. Here's like y equals x squared, which goes to infinity. You can see it's much faster. So polynomials are next, but who goes to infinity even faster than polynomials? Does anybody remember from the growth?
Exponentials?
Yes, yes. If you have an exponential, woo, that goes even faster than the polynomials do. So that's good to kind of be mindful of if you're doing limits at infinity, to keep that in mind. Now there's more here, but we're probably not going to run into you know, other things. So exponentials like e to the x and so on. So who goes to infinity faster than e to the x? Well, x to the x. So that's one. And also factorials, but we're not going to deal with factorials in this course, just to let you know. So remember, we're not going to do sequences and series either. Okay, so what is the limit as t goes to infinity of e to the negative t? If you use your direct substitution and then go to your limit facts, what is e to the negative infinity go to? Well, look at your limit facts.
0.
Yeah, that was one of my facts that I gave you there. Boom, 0. So you're done with that one. So the first component, the limit exists, boom, goes to 0. So we're done with him. Okay, next up, you have the second component, which looks like a polynomial divided by a polynomial. Now, if I use direct substitution here, I'm going to get like negative infinity squared minus 2 all over 3 times infinity squared plus 5, which is infinity over infinity. Am I allowed to use L'Hopital's? Sure.
Yeah.
Sure. I could, if I'm a smart rat, though, do a short circuit on this, because this is going to end up having repeated L'Hopital's. So does anybody remember how to short circuit this kind of problem?
Yeah.
The idea of growth rates. All right, I'm opening it up.
Yeah, you look at the leading variables of the highest power, and then you look at their coefficients.
Yeah, do you notice here the polynomials have matching degrees? And if your polynomials match in the same degree, the limit will exist and it'll be the lead coefficient all over the lead coefficient. Now, if the numerator has a lower degree than the denominator, the limit will be 0. And if the degree of the numerator is larger than the degree of the denominator, it blows up. So the limit does not exist. If you remember those 3 facts, you'll be set when you have a polynomial divided by a polynomial. So this guy's limit exists. Okay, fine. Let's go on to the last guy. So the last guy, this is where growth rates are going to come into this situation. You've got a polynomial all over a logarithm. So this is going to give me infinity over infinity. And certainly you can go ahead and use L'Hopital's and keep going and so on. But there's a quicker way to short circuit this process. I notice I have a polynomial all over a logarithm, and we both know that they both go to infinity as t goes to infinity. But who goes to infinity faster, polynomials or logarithms?
Polynomial.
So the numerator is going to infinity faster than the denominator. It's almost as if the denominator was standing still, like if it were a constant. So what is this ultimate limit going to be?
Infinity.
Yeah, it's going to be infinity. So so what does that mean for the overall answer? The final answer for this problem is the limit does not exist. D and E for short does not exist. Because this limit for the last component blew out, and if even one of the component's limits blows up like this, going to either infinity or negative infinity, you're done. The whole limit, D and E. Questions?
So when we were dealing with single variable, like regular functions, if it gone to infinity, did the limit still exist?
Not really, because it blows up. But typically you say the answer is infinity.
Oh, yeah, I remember that. Okay.
What does this mean for our final answer, though?
Right here. Just write down the words, limit does not exist. That's the answer.
So no vector
Don't give me a
brackets?
vector. Don't give me a vector. Oh, no, you better not.
Okay.
Don't you dare.
So
I
what are
don't
the
want to see
components
a
then
vector.
that doesn't?
You write down, limit does not exist. Sorry.
Well, I have a question.
Sure.
Hello?
Hello,
Can you
I
hear
can
me?
hear you.
Huh?
Adriana, go
Oh,
ahead.
hi. Yes.
Hi.
Yes, so I still have the question. I'm still confused about the last one.
Okay.
Because if t squared, the limit's going to infinity, right? And
Are you
it's
talking,
gonna
Adriana, are you talking about this one
overpower
right here? Hello? Are you talking about this question
the
right
last
here?
one.
Oh, the last one? Okay, this one right here?
Yes, the one with the limit does not exist.
Yes. It actually blows up to infinity because the polynomial goes to infinity much more quickly than the logarithm.
Oh, so is the answer is infinity?
For the last component, yes, it goes to
Yes.
infinity. Now, if you want me to do it in slow motion, Adrienne, I'll be happy to. If I apply L'Hopital's here, instead of just using my knowledge of growth rates, I could go, okay,
Oh, no.
what's the limit of the derivative of the numerator divided by the derivative of the denominator? But if you rewrite this using your algebra knowledge, so you're going to go 2t times the reciprocal, right?
Mm-hmm.
Adriana, are you watching this?
Yes.
Are you getting the feel for it?
Yes. So so I think that's good because I think it's gonna go to infinity.
Yes, you're right. But then your final answer for this whole problem you're going to write down the words limit does not exist.
Why? Why is that?
Because you can't have a vector where one of the components is infinity. Adriana?
Uh-huh.
Adriana, you
Yes.
cannot have a vector where one of the components is infinity. No, that's not legal. Okay?
Oh,
If
okay.
you still are
Okay, I
confused,
understand.
please come visit me in office hours today, and I'd be happy to do some more for you. Okay, I need to move on. Okay, I have a little meme for you. It's a little funny.
Okay, thank you.
It's I'm going to mute everybody now. They're getting very noisy out there. You guys mute yourself, please. You've got a lot of stuff happening at home. So I love this because, you know, here you've got an 8 and a 9 talking to each other, and the 9 says, hey, I'm higher than you. And then the 8 lies down and says, now what? And then this one is kind of fun for Calc 1 people. After explaining this to my students several times, you know, because 1 over 0 is infinity, I wanted to check if she really understood it. So I gave her another example. How about the limit as x approaches 5 instead of x approaching 8? And then she wrote, oh dear, that's not quite right, right? Okay, anyway, we got to go for the humor where we can. So we're now on to, we're done with limits, and if you still, you know, have questions on limits, yeah, it's the SuperCalc 2 Deluxe Edition of vector limits. Yeah, that's exactly right. So now we're on to derivatives and integrals. Now, good news and bad news about this last part. The good news is, if somebody says, hey, take the derivative of this vector valued function, you just individually take the derivatives of each of the components, knowing all that you know about derivatives, and then boom, you give the vector, because it's also good. The derivative of a vector is also a vector, and you just give the vector answer. So that's the good news. The bad news is if you're a little bit weak still or rusty with your derivative skills, or you forgot some differentiation rules, then this section is going to be a little red flag for you, and maybe it'll hopefully motivate you or inspire you to go work on beefing up some of your derivative skills. And the same goes for integrals, okay? So let's do the official definition of derivative, similar to what you saw in Calc 1, the limit definition of derivative, because all derivatives have a limit definition, period. So the derivative of a vector valued function, r prime of t, which itself is a vector, you're going to take the limit as delta t goes to 0, and then this right here is known as a difference quotient. You're going to take the difference of the vector valued function evaluated at time t plus a bit, which is a little tiny delta t, minus r of t all over delta t. And then you take the limit as delta t gets squeezed down to 0. And of course, it's assuming the limit exists, because it might not. Now, if your r prime of t exists, that means your vector valued function is indeed differentiable. And if it exists for all time in a certain interval, then it's totally differentiable on that interval. Now, if it's not differentiable, okay, that will mean something about the way that the curve looks. And you saw this in Calc 1. Like if you recall from Calc 1, what are some ways that derivatives can exist if your function is continuous? Like I'll just give you an example. Do you remember of a function in Calc 1 that has a cusp like that? It's not differentiable at that point, but it is differentiable elsewhere. So right there we have undefined derivative, and that's going to be similar for us. If you've got a vector valued function and the graph has a cusp like that one, or a sharp corner like this, like an absolute value function does, then it won't be differentiable at that sharp corner or cusp. Now, of course, it's not going to be differentiable at any asymptotes or things like that. That's a given, okay? That's still going to be in effect, just like Calc 1. So, good news, I'm not going to ever have you define limits in my class using the limit definition, although there certainly are homeworks in there, so I could have assigned them. You're welcome. Okay, So here's how we're going to do it. You're just going to find derivatives on a component by component basis and then put it all together either in component form or linear combo of the standard unit vectors, or the way my math lab may be asking you to. Now, I do want to have you watch how this limit definition ends up being component by component basis. So this is just a quick little proof on why this works. For those of you who are math majors, this is the kind of stuff, if you're a true math nerd, you get excited about this stuff. If you are an engineering major and you're like, oh, I'm not into proofs, that's fine. Although when you take complex analysis, especially you electrical engineers, because you're going to have to, you will thank me that I'm doing this for you right now, where I'm going to do sort of a breakup, because you're going to see this in your complex analysis class, but instead of breaking up by components, you'll see them do a similar thing, breaking it up with the complex portion and the pure real part of a complex function. So I'm just saying, for those of you who really care about your education and not just, oh, just give me my A, this is something worth looking into. And I'm doing you a favor by doing this, so check it out. If I break this down, what am I doing here? And I'll use the linear combo. What is R, the vector value function, when you plug in, instead of just t time, t plus a little extra? Well, it's the first component evaluated at t plus a little extra, I hat, plus the g evaluated at that little t plus delta t, j hat, so there's your r of t plus delta t, minus r of t. So he just looks like f of t I hat plus g of t j hat. And that's all over delta t for the denominator. Now what? Well, what I'm going to do now is I'm going to just rearrange this mess that's in the numerator and split it up into two pieces. So what do I mean? I'm going to take the I components, if you will, and put them together, and then plus the j component stuff and put it together. So this is really easy. I'm not doing anything mysterious here, people, but I'm testing your knowledge of Calc 1 is what I'm doing. So let's see if you really remember any Calc 1. Remember I told you this class is Calc 1 on steroids? So here's the part where you're now going to distribute this limit as t goes to 0. I'm going to distribute this limit here over each of these separate components and see if anybody remembers this. Okay, so any math nerds in the room? What does this remind you of? What can I replace that whole mess with? Something times I hat. It's a definition from Calc 1. I'll open it up to the chat. Anybody there?
Isn't
Yeah, I'm
that
here. It's just
the
pretty busy.
definition for a derivative?
Yes, that is the definition of the derivative. Thank you so much for f of t. So this whole thing is a Calc 1 definition, and I just go f prime of t times my I hat. Beautiful, beautiful. And then I'm going to have plus something else times j hat. So what do you think?
So it's G prime. Let's see.
Yes, indeed. And so this is why the limit definition totally works for vector value functions, because we're just using our knowledge of Calc 1 and definitions, the limit definition that you got from Calc 1. So that's why this next theorem, you're going to fill in the blanks. And it's real easy, because if you were paying attention to what I just did, you already know the answer. So if you have a two-dimensional vector valued function, it could be given to you in component form or as a linear combination of the standard unit vectors. Then r prime, and I want to see this notation here. See this arrow over the r prime? you still please do that on all of your handwritten uploaded work, else I'm going to continue to take points away until you get this notation down. So this is going to be equal to one of two things. You could either write it as a linear combination of the standard unit vectors, or you could write it in component form. I always like component form myself if I'm given a choice. This is my favorite. But sometimes my math lab may want you to rewrite it as the other format. And then if you have a 3D vector valued function, no problem there. Your R prime is going to be one that has the K, the K hat. And if you prefer, you can put it in component form, which I like. I'm running out of room. Okay, so there is the official theorem, differentiation of vector valued functions. That's it. Now I'm just going to do a lot of examples that involve derivatives and derivative rules and so on. So hopefully, I'm hoping that this will benefit you as far as seeing maybe some of the rules in place. And we, you know, I gave you guys a quiz zero, 2 quiz zeros at the beginning of this semester to help you refresh your Calc 1 and Calc 2 derivative and integration skills, and hopefully that's still fresh, but if not, here we go. So the derivative of a vector valued function, R, is itself a vector valued function. And so I hope you can see that this difference quotient is found by taking the difference of these two vectors here, where you connect the tips, and I did the subtraction of 2 vectors is going to give you a vector connecting 2 tips of the vector. And then when you divide it by delta t, you're basically squeezing down the distance between these 2 vectors. So this vector here will start getting closer and closer and closer to the other vector. So that's where you find the limit. So what do you end up getting? What is, visually speaking, and if you don't get this key fact, you're going to be totally hurting for basically the rest of the semester. So I want you to get this pictorially speaking. R prime, you see this, here's your curve right here. This is the graph of the vector valued function, not the derivative, the original vector valued function. The derivative R prime, which itself is a vector, let's say you're finding R prime right at that point. It's going to be a vector tangent to the curve. This is key. Know this. And of course, there's multiple R primes. So like if I were to draw all the little R primes for this red curve here, you know, over here, I'm going to draw a tangent vector. You know, over here, I could draw another tangent vector. Over here, it's going to start pointing a little bit down. If I keep the red curve going, let's just assume the red curve kind of goes down like this, just say. So the red curve is going to head downward. Then all the little R primes, if I continue to draw tangent vectors, ooh, I don't know how I got that color. Get a little bit brighter here. And so this R prime is tangent, so he's kind of going down. So all of these little blue vectors I'm drawing are R prime vectors. Because R prime changes, you know, just like when you got derivatives from Calc 1, which basically gave you slope, those slopes can vary depending on the graph. And similarly here, the R prime is going to change magnitude and change direction depending on where you're taking the derivative, at what point on that curve. So, but it's always going to be tangent to your curve. So that's key that you know, visually speaking, what R prime is doing here, visually with the eyeballs. And if you don't understand this, when we do some applications of vector valued functions, which is probably going to happen in the next week, involving projectile motion, and that's where I think your midterm is going to have 14.3 on it. That's going to be projectile motion. You have to get that your derivative for the projectile motion function is going to be tangent to the line of motion, essentially. And this is where I'm going to catch some of you again, and I mentioned this Wednesday, but I'm going to mention it again. Some of you are reluctant to use the knowledge that I'm going over in this course to do certain problems, and you're using physics strategies. and oh, well, I got the right answer. Well, I'm going to continue to take massive amounts of points away from you if you don't use the approach here in my lecture, which is the approach in the book, the text, as well as what's on my math lab. So please do it this way. All right, so let's do some derivatives. Here we go. We'll start with a really easy one. I'm never going to give you something this easy on any of my quizzes or exams. Just to let you know, we're going to start off easy just to boost your self-esteem. Okay, so what is R prime? It's going to be a vector, and it's going to be a vector that will also have 3 components because the original vector did, and you just have to put the derivatives of each of the corresponding components. So what is the derivative of 1 over t?
-1/t squared.
Okay, good. I was thinking somebody might say, oh, that's ln of t. You know, you're like, whoa, whoa, now you're taking integrals, not derivatives. So be careful. Yeah, so if you take the derivative d dt of 1 over t, you're really saying, I like to use the power rule, so I rewrite that as t to the -1 power, and that's equal to -1 times t to the -2. And when you write your final answer, if you can, please rewrite with positive exponents only, except for exponentials. I don't need you to rewrite exponentials with positive exponents. In other words, I'm totally okay